So basically in last class, we started unsupervised learning, and we discussed the space or the understanding of what is supervised learning, what is unsupervised learning. We also discussed that within unsupervised learning, we have clustering as our main objective. Of course, there are other things that we can do with unsupervised, but at this level of our understanding and our journey, clustering is the next logical step to look into. We saw what is clustering, we saw some of the major approaches for clustering, and I think that is where we had stopped the discussion. Let me go ahead. So clustering is basically a part of unsupervised learning where we are trying to group similar objects together. This grouping can be based on different features like height, weight, and so on. We also saw that this grouping can be done in two kinds. That is either distance-based or conceptual. The distance-based is where we are measuring geometrical distance using Euclidean or Manhattan methods, which is also L1 norm and L2 norm. Or it can be conceptual. That is, we are looking at descriptive concepts and we are trying to group them together. Like for age feature, descriptive concepts would mean like young, middle-aged, teenager, and so on. We saw different examples of clustering, and we also said that okay, if we have to make 4 clusters out of this, there are so many different options. Which one is right? And then we saw that okay, uh, the right part of clustering is not a very clear idea. It is actually depends on a lot of scenarios. So what we truly want is to go for something called as intrinsic grouping, that is trying to find out what is the pattern uh, of grouping within the data itself. We also saw that there is no best criteria as such. It is subjective depending upon what the data is and what field it represents, and what we can do is probably take help from the domain expert, and the domain expert will give an idea depending upon the application what is the right set of clusters to go for. We saw examples of or we saw applications, some possible applications of clustering like data reduction, finding natural clusters and defining their unknown properties, or finding useful and suitable groupings. Finally, finding useful objects, uh, unusual objects using something called as outlier reduction. So outlier detection, even under the same category, we add one more group called as outlier reduction. So one more group is anomaly detection. Okay, which basically means that we have lots of nominal data, and from that nominal data we are trying to learn to understand what does it mean to be normal, and anything that is way apart from this part, that is way apart from normality, we would group as abnormal or anomalies. And this kind of data is used for tracking uh, uh, abnormalities in a usage pattern, and based on that, triggering an alert sign. So I think I discussed about the Google example. That is, normally when you log in from your home device, you would not see any error, or you would not get a trigger or some kind. But when you either try to access from a new device or you try to access it in a different pattern, it will probably push you an error saying, or push you an either an alert or extra authentication depending on that. So again, this is also an example of outlier detection or anomaly detection. Okay. So going ahead, once we understand the needs of clustering, there are 4 kinds of approaches for clustering. One is called as exclusive, and exclusive, agglomerative, overlapping, and probabilistic. And looking at the diagram, we can get some kind of idea of what these type of clustering is. So if you look at the first one, which is exclusive clustering, you can see that we have individual clusters. So finally, after the grouping is done, we can see that uh, the clusters, they do not overlap in any way. They are completely separable. Okay, they're completely exclusive. What this means is, if an item belongs to group belongs to the blue color, then it definitely does not belong to the red color. It only belongs to one group at a time. There are individual clusters and there is no overlap. One such example of a method of an unsupervised learning method that does that is called as K-means clustering. Similarly, we see in agglomerative clustering, the scenario is something else. We see that multiple uh, hierarchies of clustering exists. So if you are at the lowest hierarchy, you may be probably unique, but all all data points ultimately belong to one group. So let's say you see in this case, we have a blue rectangle and all data points belong to that. Within that blue rectangle, we have further two subsections. One is this red and one is this yellow. And we can say that these are again then two clusters. And further within the red cluster, there are two clusters again. Okay. So here we see that there can be different hierarchies of clustering, and one data point may be part of multiple clusters depending on hierarchy. Okay. So this maybe a point like here would be part of this blue cluster. It is also a part of this a bigger group called as the red cluster, and then again it's part of the universal cluster as well. So each data point will be part of different clusters on different hierarchies. Okay, which is not the case with exclusive. Exclusive, there's just one data point belongs to only one cluster. Then we have overlapping method where uh, okay, for agglomerative, the algorithm that we use is called as hierarchical clustering. Okay. Then we have an overlapping clustering where you can see that though there are different groups, there is some level of overlap between multiple groups. Or we can say that there is something called as degrees of membership. Each data point belongs to all the three groups in different quantities. Let's say a data point here would say that it belongs 99% to blue group, 0.5% to red group, and 0.5% to this group. Okay. Or let's say you are somewhere in between, you would say maybe 51 and 0, or 50 and 0, or 49 and 1, and so on. So we can see that here we are actually talking about degrees of membership, and each data point belongs to all the different groups in different levels of membership. One such algorithm that helps us to do this kind of overlap-based kind of clustering is called as fuzzy C-means clustering. And finally, we have a probabilistic clustering, which uses distribution. So here also a similar idea like overlapping, but more on the distribution of the data based. Okay. So in our study here, we'll be focusing on exclusive and agglomerative, and we'll look at these two algorithms, the K-means clustering algorithm and the hierarchical clustering algorithm. Going ahead, let's look at exclusive clustering. Okay. So for exclusive clustering, our aim is basically to partition the database D of n objects into K clusters. So we have all of our data. We have n different data points, and our aim is to divide them into K different clusters. So the method that it works on is, given a value of K, we are trying to find a partition. We are trying to partition K clusters that optimizes the chosen partitioning criteria. So depending upon the chosen partitioning criteria, we are trying to optimize this or divide the clusters accordingly. Uh, Here we'll be using a very old algorithm, which was which was suggested by Kmeans in 1967. So it is one of the, since it was so old, it is one of the commonly used algorithms, Kmeans, and it's basically a heuristic method where each cluster is represented by the center of the cluster, which is centroid. So basically, when you look at a group of data points, we'll say, okay, let me find the centroid of the data points. That is, I take, let's say, here we have x coordinate and y coordinate. We take all the x coordinates, all the y coordinates of all the data points that represent a cluster and try to find its centroid. So that would mean the average x component, the average y component, and then as many other dimensions are there, that value represents the centroid. So we'll do this for all the clusters, and we'll say that, okay, instead of the cluster being represented by multiple data points, we have a unique representation of the cluster, that is the cluster centroid, and we use that for our calculations. So let me okay. So we look at K-means clustering algorithms. So given the value of K, the K-means algorithm is implemented in 4 steps. First is, we choose K points at random as cluster centers. So you have all of your data. Randomly, we select K points. So if we have to divide this into maybe 4 clusters, we randomly choose 4 different points of the data as cluster centers. Now, for those 4 points, we will measure all the other data points which are closest. And if they are closest to any of the 4, we will assign it to one of those clusters. So assign each instance to its closest cluster center using certain distance measurements. Okay. Using a certain distance measurement. So the distance measurement can be Euclidean, Manhattan. So it can be conceptual also, but for now we'll just focus on numerical methods, because assigning distance or measuring distance for numerical methods is more natural. Okay. Once we have assigned everything, now we have 4 different clusters. So for these 4 different clusters, we'll recalculate what is the centroid. So now there are new points added to this each cluster, and with these new additional points, we can recalculate the value of centroid. And of course, the centroid will move so long as the clusters are unstable. Okay. So the cluster centroids will move, and we will have a new cluster centroid. Okay. So with that new cluster centroid, we'll go back to step 2, and we'll assign again other set of data points into that cluster. Okay, and we will keep doing that till the cluster centers don't change anymore. Once they don't change anymore, we know that we have found a stable cluster definition. So to see that idea, we can look at this graphic with us. So notice these points, choose the centroid, assign based on distance, recalculate centroid, and repeat till it settles. So in this case, you can see that the green, 4 green points, they represent the cluster centroids. Okay. Let me see if we can start. Okay. So at this point, we are basically, let me zoom this. So all of these data points are there. We are randomly choosing. Okay, we are randomly choosing 4 data points. Okay, 4 points as cluster centroids. We choose 1, 2, 3, and 4. Now, for these 4 points, we are measuring the distance of every other point with these points. So, if I take this point is closest to this cluster centroid. Okay, compared to this 1, 2, 3, 4, the closest one is this. Since this is the closest one, we'll assign this data point to this cluster. You look at this data point, again, this is the closest one. We assign it to this cluster. This data point, again, this is the closest one, so we assign it to this cluster. What about this data point? So this data point is closest to this second cluster, we assign it here. So we look for all the other data points, and depending on which is the closest of the 4 centroids that we selected earlier, we'll assign it accordingly. Okay. So once we assign it, let me go Go ahead. Okay. Then we see in the next phase that for the chosen centroid that we saw, for the chosen data points for that particular cluster, now the centroid will change. In step 2, we'll say, okay, if all of these are in one group, what is their average? So average will take all the x coordinates of all these data points, add them, take its average, take the y coordinate of all these data points, and take its average, and then our cluster centroid. Earlier, this one was here. It has moved to this new location. This new location may not be a, may not have any data point, but we can use the conceptual x and y to represent the unique cluster centroid. So that data, that cluster head, it moves from this to here for all these cases. Okay. So this was somewhere here. We have new data points, so it has moved to the top. This goes up. Going ahead, you see at every step that cluster centroid keeps on moving depending upon who is the or what are the selected data points. So in this case, once we reach till the end, okay, once we reach till the end, we can see that now we have 4 different clusters. Okay, this would be cluster 1, cluster 2, cluster 3, and cluster 4. And we can see that these 4 clusters, they at this moment, at least the way they are grouped, it seems that they form good clusters where there is separation between the data points, and it seems that this could be the right option. Okay. Does this make sense? How this clustering is done? Okay. So let me go back to screen. So the idea is simple. Choose the centroid, assign distance, or assign the each of the data points to the 4 centroids that we have based on how close they are, based on distance. Then recalculate the centroid and repeat till settings. The only problem with this method is, let's say we start with this 4 random points. What will happen if we start with some other random points? Will our model have similar uh, clusters in the end, or will the clusters change? So let us look at that. So if I take the 4 most left points, you see how my cluster is moving. And now in the end, once we have divided the clusters, we can see that this clustering is different from the first clustering. If I start from 4 right points, I again end up with 4 different clusters. In fact, I have one cluster here that is just stagnant. It is not moving at all because it never got an opportunity of any other clusters, any other data points which were close to this. Start from 4 top data points. We're left with this cluster, and 4 bottom, we're left with this cluster. Okay. So we saw multiple cases where our different data points can be clustered differently. So now looking at this, we can probably try and discuss the strengths and weaknesses of K-means algorithm. Okay. So few strengths are, it is relatively efficient, which is basically it means that it settles down very fast. You don't need multiple iterations for it to settle down. So in this case, if you see, we have roughly maybe I think 50-60 data points. For these 50-60 data points and 4 4 clusters that we have to form, can we count, or can we at least try to attempt how many iterations it is taking? So there's iteration 1, 2, 3, 4. Yes, I think around 4 iterations. This is so fast. Uh, I don't know if I can slow this animation. The only control I have is, I think, play pause. Fine. So this is, let's say, iteration 1, where we start with 4 data points. Now we are assigning everything. Okay, so that will be iteration 1. Okay, so there's iteration 2 that we have moved to a new point, and then we are again we'll be assigning the new cluster point, iteration 2, and the next is 3. Yeah, I think it's just 4 iterations, and within 4 iterations, the green points they stop moving. So here we see basically the advantage. That is, let me go ahead. That is, it is relatively efficient. Okay, so even if there are n data objects and there are k clusters for t iterations, your k and t are generally very less compared to n. Okay, you will have very less clusters, and for those very less clusters you will have very less iterations. Okay? So that is one advantage of K-means. It is relatively efficient. Second is the procedure always terminates successfully. Okay. Irrespective of how many clusters you start with, you will always have an answer. You will never. It will never be the case where your iterations will continue to. It will never stop. It will never happen that your iterations will continuously, keep searching for new clusters and never stop. We have a fixed idea, and as our clusters move very quickly, we see that it settles down to a stable answer. So the procedure, it always terminates successfully. What are the few weaknesses then? Okay. Few weaknesses are, it does not necessarily find the most optimal configuration. Right? In fact, we saw that with multiple runs and starting with different random points, our data can be clustered separately, or it can be clustered in a different way every time. So that basically says that if you run the algorithm multiple times, you may not end up with same clusters. And if you do not end up with same clusters, your algorithm is basically not reproducible. So multiple teams may use up the same algorithm but get different answers, and that is not a very safe choice to operate on. So that is which is a problem, or which is a weakness of K-means. Uh, Thirdly, it is only applicable when mean is defined, and that is it can be computed. So as long as you can define the mean of the features, okay, then we can move the centroids, then we can talk about distances and so on. If mean has no conception, there is like looking at the data, we cannot say what is the mean value. Then it is very difficult to work with K-means algorithm. Okay. So by mean, basically what we mean is if we have numerical data, K-means is actually applicable. But if we have categorical data, it is very difficult to implement K-means. Finally, we need to specify K, that is a number of clusters in advance. Even before starting the process of clustering, we have to tell how many clusters exist within the data. And whatever K value we give, only for that K value, it can find the clusters. Okay. So basically, there is no intrinsic finding of how the clusters are divided. Okay. Or the model will not tell us intrinsically that this data can be divided into 3 or 4 or 5 clusters, and these are the clusters. We have to guess what should be the cluster beginning, or how many clusters are there, and based on that, the clusters will be divided. So that is definitely a con, because uh, we as humans are can be mistaken in how many clusters are there, if there are, because we cannot see in multiple dimensions. That is the problem. But in cases where, let's say, we know we have to develop 3 clusters or so on, then we can use K-means algorithm very efficiently. My iPad is starting. I will connect this here. Just 1 second. Okay, so we saw strengths and we also saw weaknesses of the Kmeans algorithm. So let's go ahead. Let's look at another algorithm before actually trying to implement any cases, so that we can do both at one go. So we're looking at the next set of algorithm, which is hierarchical clustering. Okay, before going ahead, do you have any questions with K-means? Is this fine? Okay, okay. Let me talk about hierarchical clustering then. So hierarchical clustering is basically a general family of different clustering algorithms, where the idea is that we build nested clusters by merging and splitting recursively. So we can build nested clusters by merging. That means we start with all individual different clusters, and then we group them together, and then we group further them together, and then them together. That is one kind of way. That is, we can build nested clusters by merging. The other option is we can build nested clusters by splitting. That is, we have all of our data points. We start with one big cluster, and we say this cluster can be divided into two parts, and then each of them will be divided into one part and so on. So that is other kind of way. That is, we can uh, create clusters by splitting them recursively. Let me remind you that hierarchical clustering is part of agglomerative clustering, which basically says that each data point uh, can be grouped into different levels of hierarchies, and each data point can thus become part of multiple different clusters. So there are two types here: agglomerative clustering, which follows a bottoms-up approach. The bottoms-up approach means we start with individual clusters and then we start merging them together. Or we can do something called as divisive clustering, which follows a top-down approach. We have a big cluster and then we start breaking them down into smaller and smaller. Let's look at this very simple example. So in this example, we have four subjects: biology, physics, history, and geography. We can see that, let's say for the bottoms up approach, we start with our individual clusters and then we say, okay, maybe history, geography, they get merged together in one group called as social science, and biology and physics can be merged in one group called as science. And we see that all of this can be merged in another group called as subjects. So if we take a bottoms down approach, we're basically going from individual subjects to groups of subjects to all subjects together. In contrast to that, a top-down approach is we say that all of these data belongs to one group called as subjects. Then we look at subgroups within that data points, and then finally we look at individual data objects as individual clusters. Okay. Both of these approaches will give us the same answer. It is difficult to say which one is better out of these. We will go for bottoms-up approach to explain the next one. So here, for bottoms-up approach, uh, that is how do we work it out? Okay, so agglomerative clustering. The agglomeration does not require k as an input. Okay? We do not need to know how many clusters we need to divide in. Okay, for all the data points, we will always end up with the same case. That is, as we start clustering our data points, we can see that. We don't need the value of k to start off with. So depending, let's say we are doing for bottoms up approach, all the data points will be their individual clusters. In the next step, we'll join or we'll merge the closest. Then we'll merge the next closest. Then we'll merge the next closest. So each step we'll keep on merging multiple clusters together. Thereby we'll have one representation. So agglomeration starts out by forming each data as one cluster. Okay, so it starts out by saying that each data is one cluster. So if we have n objects, we'll have n clusters. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 data points, and thus we have 11 clusters at iteration 1. Next, we reduce the number of clusters, one in each iteration, by merging. So we'll find out what are the closest to. So I'm guessing these two are the closest. Okay, so we'll merge them together and we'll say this is one cluster. Okay. That's the idea. We reduce the number of clusters, one in each iteration. In one iteration, we will just merge these two. The next iteration, we'll see what is the next closest, then merge them. Next iteration, we'll see what is the next closest, merge them, and so on. Okay. As we keep doing that, we are reducing the number of clusters, one in each iteration. Finally, we will be left with one big cluster that contains all the objects. Okay, one big cluster that contains all the objects. The question then is this: what is the point of having one big cluster in the end? What is the purpose of getting this cluster? Since generally when we say clustering, we want a separation between the grouping. We need to know how the data is grouped. Okay. So before going there, let me try to show you how this clustering will work out. So if I have to draw clusters, I'll say okay. The closest one is these two guys. So we will say this forms one cluster. Next, we would say that these two are the closest. So we'll form this cluster. Uh, I'm just copying this animation that I have here. Then this forms a cluster. Okay. This one, this one, this one, this one, this one, this one, and then finally this one. So at each iteration, we will look at the closest data points and we'll start grouping them together as clusters. So I hope this is clear how we are forming the clusters, but this may not be clear so far as what is the purpose of this exercise. So let me go there. Uh, the purpose of this exercise is, as we are drawing these clusters, we are also making another diagram called as a dendrogram. And this dendrogram will further then help us to choose out of all these different clusters. It will help us to choose what is the number of cluster heads we want, what is the number of clustering we want, and then based on that, what those clusters are. So here again, I'm just defining what the steps are. Assign each item to its own cluster, compute pairwise distance between the clusters, merge the closest two clusters into a combined cluster, and repeat steps 2 or 3 till only one cluster is left. That is the idea. Now, cut the tree depending on how many clusters you require. So this tree that I'm referring to is coming from the dendrogram. Let me show you what the dendrogram looks like. So a dendrogram is basically, as we are clustering here, we will try to form this tree, this dendrogram structure. And what this dendrogram structure is, basically it represents when we are joining two objects together, it will say that these objects are connected here. Okay? It gives us the structure of how these data points are. Let me show how this example works out. So within this example, we have uh, we have 7 data points: P0, P1, P2, P3, P4, P5, P6. And within our clustering, what we would do is we'll say, okay, the closest two data points are these P5 and P6, so we'll group them together. And as we group them together, we also mark it here. So we'll say that all data points will write it on the x-axis. So P0, P1, P2, P3, P4, P5, P6. And we see that P5 and P6 are the closest. So we'll join them together using this line. Now within this line, this height here represents the distance between 5 and 6. The distance between P5 and P6 is represented by what is the height we are using for joining these two together. Okay. So we say, okay, let me join P5, P6. Then we say, now we have how many clusters? We have 1, 2, 3, 4, 5, 6. Instead of 7 clusters, now we have only 6 clusters. For these 6 clusters, what are the next clusters closest? So we see that, okay, this is the next closest cluster. So we mark it. Okay. After marking it, we also mark it here on the dendrogram. So we see that, okay, this is cluster 1, this is cluster 2. The closest, or the distance between these two guys is this much. So we say, let me join them together. We'll say P4, P5, P6 will join with this tree structure. Then we find out, okay, what is the next closest structure? So we'll say this is the next closest structure. So we will group them, and as we group them, we mark it up here. This is our P3. Okay, sorry. The next closest structure is not this one. The next closest structure is actually, see, after we have to look at the horizontal lines. So this next closest structure is P1 and P2. So they say, okay, P1, P2 are close, so we will join them. As we join them, we mark it here. So we mark this height represents that they are pretty far compared to these guys. They are pretty far, so we'll merge them based on this distance, and we'll write down this distance here. Okay. Then we see the next group is this distance between P0 and this cluster center, P1, P2. So we'll merge them together. And we'll merge these guys together. And then finally we'll take one big cluster and add all of these guys. So the interesting thing is this is the same as what we did earlier, but along with merging them, we are also drawing this structure. Okay. And then once we have this structure, one very important use of this structure is we can now choose how many clusters we want, and based on how many clusters we want, we can get it from this diagram. Let me show you an example. Let's say we are interested that I want only 2 clusters. Okay. So if I want 2 clusters, I will draw a horizontal line, and I should ensure that the horizontal line cuts in 2 data points. So if I draw a line, let's say here, I can see that it cuts in 2 points, and this will be the 2 points that I will use for my cluster. So everything that follows under this will become cluster 1. Everything that follows under this will become cluster 2. In this case, P0, P1, P2 is one cluster. P3, P4, P5, P6 is one cluster. So I'm talking at this level. So I have just 2 clusters, P0, P1, P2, and then P3, P4, P5, P6. Does this make sense? Now instead, if I want 3 clusters, what we could do is, instead of cutting here, we would cut at the next point. I would say that, okay, I want 3 clusters. So now my data is cutting into 3 points. So everything here belongs to one cluster. So this is same P0, P1, P2. P3 is an individual cluster, which means that I'll be deleting this grouping. I'll say P3 is one cluster. And then I would say that here P4, P5, P6 is one cluster. So now we have again 3 cluster points. Okay, we were able to get that not by recalculating. Once we have the dendrogram, we can directly use the dendrogram to get as many clusters as one. If I want 4 clusters, I have to draw this line, which will cut my dendrogram in 4 points, 1, 2, 3, and 4. And for these 4 points, then we can say what the clusters are. So that is P0 will be an initial cluster, so I have to delete this grouping. Now we have 4 clusters. P0 is one cluster, P1, P2 is one cluster, P3 is one cluster, and then P4, P5, P6 is one cluster. I hope this makes sense. Have you got this part? Okay, excellent. Okay. So now we saw how we can use agglomerative clustering, and we can end up with this dendrogram, which helps us to find out how we can get multiple clusters from our data point. Now, once we are having these clusters, let's say I want to, while forming the cluster actually, we said to find the next closest cluster. How do I know what is the distance between these guys? This is one cluster, this is second other cluster. What is the distance? And this distance can be actually calculated in several different ways. Let me show you examples. So we have this distance based on something called a single linkage, average linkage, complete linkage, and water linkage. What does that mean? So simple linkage means we will look at between the 2 clusters. So what is the closest data point? So let me, in this case, we'll say that, let's say that, let me try, find the closest cluster here. Okay, so here we have two clusters. This is cluster 1, this is cluster 2. So from cluster 2, closest one here is this one. So we would say that this will be the distance between the two clusters. That is using single linkage, the closest between 2 points. Complete linkage is basically the farthest points. So between these two clusters, what is the farthest distance? So here we have one within this cluster, one data point here, one data point here, and the distance between these two guys is called as complete linkage. So we can use again that for our clustering. We can have average linkage, that is we will find the distance between one data point with all other data points that measure one distance, and one data point with all other data points, then measure distance. I've not drawn it this way, but from each data point, distance to all the other data points, and we'll find the average of all such things, and we find something called as average linkage. So that can also be the distance measurement between these two clusters. Or we can have something called as word linkage. What is word linkage is, we will take all of these points and we'll represent them using one centroid. Once we represent them using one centroid, here also we represent using one centroid, and then we find the distance between these two centroids, and that is word linkage. As we choose different methods of computing distance, our grouping can be our grouping can be very sensitive to it. A grouping can be very different based on such different clusterings. Okay. This is an example of hierarchical clustering. I'm just writing some piece of code as an algorithm to explain. Maybe we can keep this for the next class, and we will look into how this works out in the next class. Okay. Do you have any questions for now? Okay. In that case, let us stop for today. I'll upload the material on our classroom, so you can go and revise and start preparing, so that we can have some better understanding for the next class. Also, I would encourage that we talked about one data set in 1 week, so keep practicing on different data sets. At least on Kaggle, I have uploaded multiple options where you can practice. The more you practice, the more you'll become comfortable in using data science. Okay. Let me stop sharing.